All right, so here's where we were last time. We were talking about parameterizations of surfaces, and I made the observation that if you have a surface parameterization, but if you then fix one of the variables, let's say we fix t, then it's not really a variable anymore, is it? I mean, it's a constant. And so what you really have at that point is position as a function of, well, really only one actual variable. That's a curve. Right? And so in particular, what we call this, when position is a function of just s of s and t, we call this the s coordinate curve of that parameterization. And then likewise, analogously, t coordinate curve. Okay, so we talked about the example here. So if let's just to get the ball rolling and see one in real life. Here's a parameterization of the sphere. Right, this is the usual rho equals 1 spherical graph parameterization. Make sure that you're comfortable with how to create that of the sphere. And I believe we talked through the theta coordinate curve. So let me now do the phi coordinate curve. The idea of the phi coordinate curve is that you hold theta constant. So we're going to fix theta at pi over 4, not allowed to change. Phi can then vary, and as phi varies, keep in mind theta being constant, theta being this value pi over 4 means that we're stuck on this pi over 4 half plane. And as phi increases, we kind of go down like that. So that's our phi coordinate curve. Okay. Alrighty. So, neat observation. If you were to take a partial derivative of your surface parameterization, I claim that's actually the same thing as taking a velocity of one of these coordinate curves. Now, I want to talk through why this is. It's not immediately obvious why this would be true. Let's talk first about what is one of these curves. Well, keep in mind they're coordinate curves. That means we're going to hold one of the variables constant. That's the first thing that we do when we take a partial derivative. We hold one of the variables constant. Right? So right off the bat, when you start to break down what each of these phrases means, they start in exactly the same way. Coordinate curve, hold one of the variables constant. Partial derivative, hold one of the variables constant. All right, next thing. What do you do when you're taking a velocity of a coordinate curve? Well, you're taking the derivative with respect to the remaining variable. The derivative with respect to the only parameter that is part of that coordinate curve. That's what you do when you're taking a partial derivative as well. So computationally, these are the exact same methods. Just kind of, we're viewing them in sort of a different way. So hopefully no surprise in that these are actually the same thing. Now the way I'm going to use that is by interpreting then, for example, this thing right here, x theta, that is a partial derivative, right? That's the partial derivative of the parameterization with respect to theta. But of course, what that is also now, we see that as a velocity. That's the velocity of the parameterization as you move in the theta direction, you might say. And one nice thing about velocities is that if you multiply a velocity times an input change, think kind of dt here, right? This is the input differential of the one parameter that we have, effectively the time parameter for our theta coordinate curve. That's the input change, d theta, right? Then this product is the corresponding output change. So this interpretation here comes out of thinking of the partial derivative as being a velocity. Okay, so nice fact then. We can look at differentials, sort of output differentials in the target as being defined by these formulas right here. They're just partial derivative times parameter differentials. Those are your little position differentials on the surface. Okay. All right. So now, with that in mind, we are fully armed to be able to compute this area right here, this little piece of output area on our surface. How are we going to compute that little piece of output area? Well, it's approximately a little parallelogram, and I know its edges. I know, for example, this edge right here, that edge is x theta d theta, right, per the calculation on the previous page. This edge right here, that is x phi d phi. And when you know both of the little edges, the area of the parallelogram defined by those two edges is the magnitude of the cross product. Old formula from, well, either Math 218 or Chapter 1 of this course, whichever you prefer. But that's, anyway, a formula for how to compute that little piece of area ds. And with that done, we can play some little algebraic games. Remember, cross products and magnitudes, scalars will factor right out. I can factor out the d phi, factor out the d theta, and the really wonderful punchline then is I now have a handy dandy formula relating output area to, well, what is in fact input area, right? So I inadvertently, just by kind of playing games with coordinate curves and thinking, well, what does this mean? And okay, what else can I do here? Notice I've got this relationship between this area in the output of the parameterization, this area in the input to the parameterization. Said differently, the factor here, this thing right here, is our area stretching factor. It's what you multiply by green area to get blue area. And it's the exact same sort of concept of stretching factor that we've used in previous circumstances. We used it with change of variables and previously with line integrals as well. So there it is. Nice little formula. Make sure to memorize this formula. Very important formula. We're going to use it a lot in various different places. Now I'm going to introduce some terminology and notation. This vector, and I emphasize, I'm talking about the vector here, not the magnitude of the vector, but the vector itself is going to be useful in several different places. I need from it more than just its magnitude, as it turns out. So this is worth having a name. First thing I'll observe about it, it is perpendicular to those two tangent vectors, and therefore it's a normal vector. Secondly, it's a normal vector that is an immediate consequence. It comes straight out of the parameterization. It's a computation from the parameterization. You can literally see we are taking the parameterization itself and taking various partials, doing a cross product, but it all comes out of the parameterization. So I call this the parametrized normal vector. FYI, just a heads up, the book prefers to call this the standard normal vector. My complaint with this is that it would be easy to confuse this term, standard, with some sort of a suggestion that this normal vector, capital N, is standard for the surface. It's not. This thing here depends on the parameterization. There's lots of parameterizations for a surface. Tons of them, right? Countless different parameterizations. You'll get all sorts of different, they'll all be perpendicular, but they'll all be different vectors, perhaps, all for the same surface. So to me, the word standard here is a little bit dangerous, a little potentially misleading. So I like to call it the parameterized normal vector to indicate that it comes from the parameterization. And I think that's a natural choice of words. Okay. All right, so parameterized normal vector, capital N. And with that in mind, our stretching factor, keep in mind here's our stretching factor. We can rewrite our stretching factor like that. After all, this thing whose magnitude we're talking about is capital N. Okay, So let's use this to actually compute something, and specifically we're going to compute the area of the unit sphere. This is a very straightforward calculation. Let me skip down to the bottom just for sort of big picture. We're going to chop up the surface area of the unit sphere, keep in mind, into a bunch of little pieces. The whole is the sum of the parts. Of course it is. It always is, right? For the right kinds of quantities. And area has this feature. You take a whole area, chop it up into little pieces, the whole is the sum of the parts. Okay. So, we also know from calculation that we just did that little piece of output area relates to the little piece of input area by way of our stretching factor. So, in order to be able to finish this calculation, we're going to need to know what is our area stretching factor for, well, we're going to need some parameterization then of this sphere. All right, so with the idea in mind that we're going to need this, let's rewind to the very beginning. Let's ask, how do we parameterize the unit sphere? Okay, we've already got that, right? We've parameterized the unit sphere several times. This is our rho equals 1 spherical graph parameterization. We talked about this one last time. Make sure you're good with that, both specifically for this example and in general for that method. And we compute, per the usual formula, various partials, right, with respect to the input parameters. We take the cross product of those partials. Some algebra to be done there. It's a healthy exercise. Everybody should do this. Again, once in your lives. I've already done mine. It's your turn. Give it a shot. It's not that bad. It's just a matter of kind of going through the cross product. And then you need to take the magnitude of this capital N vector that we just computed. And this is another calculation that everybody should do once in their lives. It's a good application, by the way, of the Pythagorean identity. I think if I remember correctly, the Pythagorean identity comes up like at least 3 times. So what looks like it could be horrendous, right? You see this vector here, and you're thinking, oh my gosh, the magnitude of this is going to be a massive expression. It'll go all the way across the page. It simplifies massively down to just sine phi. So this stretching factor is just sine phi. We end up then with a very straightforward double integral to compute, and it ends up being 4 pi. So, nice little calculation. Oh, by the way, of course, we already know from high school geometry class that I was just trying to make sure that was in all the way. This is the correct answer for the area of a unit sphere, and this is a confirmation as a starter example. Okay. All right. Okay, so summarizing, there's very little new on this page, but a parameterization allows you to take a surface, just a sort of a standalone surface, and kind of get your foot in the door and compute things like these various partials and their cross product, and this little area comes out as a result of it, and stretching factor, et cetera, et cetera. So the formulas are all down here. What I'm going to point out on this algebra is that this cross product, you could, I suppose, write it out in coordinates, and you can crank out the cross product coordinate-wise. Just literally compute the coordinates of that cross product. It's, a couple of, multiplications and subtractions, basically. And what's kind of interesting is it turns out that means that this capital N vector has coordinates which are area stretching factors for like a 2x2 change of variables. That's very unexpected. Where's the 2x2 change of variables in this picture? Right? It's hard. I don't see immediately any 2x2 change of variables. And yet, look, again, these coordinates are exactly 2x2 Jacobian determinants. Turns out this is not a coincidence, but it is something whose explanation requires more time than we have to give. If this were a full year course, I would go into great detail as to what this is good for and how this is useful. And sadly, we don't have that time. So, anyway, if you're curious, I'd be very happy to talk about this in office hours, but we're just going to let that sit there. Okay. All right. Now, there's a really nice special case that we need to talk about. Keep in mind, we have our formula for our stretching factor. It's the magnitude of capital N. This is the formula. This is the one you need to make sure that you know. Magnitude of capital N. And, of course, don't forget capital N itself is the cross product with the partials. Okay. Got to know that for sure. But very often you're using a graph parameterization. When you are, your graph parameterization will always look exactly like this. Which means that your partials will always look exactly like that. Which means that your cross product will always look exactly like this. Which means the magnitude will always be exactly that. So, you could, I suppose, compute that every time. There's a school of thought there that says compute it every time, but there's also a school of thought that says, look, if it's always going to be this, how about I just memorize this? I think it's a nice little time saver. I encourage you to memorize this formula and to use this formula when you can. What's very, very important, and what a lot of students underappreciate, is that this only works if you are using a graph parameterization. That's only if you're using a graph parameter. If you're parameterizing some other way, right? So for example, up here, this example here, this parameterization is not a graph parameterization. It's a spherical graph parameterization, but z is not a function of x and y. It's a sphere. You can't solve for z as a function of x and y. You cannot use that formula for this. Right? And for many others. Again, not every parameterization is a graph parameterization. So, great formula, nice to have, nice little time saver in the circumstances it applies, but again, it only applies sometimes. How we doing? Is everybody happy? Okay. All right. So, quick observation, this is the magnitude squared of the gradient. Just observe, right? Easy to check. Then you notice, hey, check it out. This thing here that I'm squaring is the steepness. The magnitude of the gradient tells you how steep the graph is. So this gives you an alternative nice formula, might say interpretation of our area stretching factor. It's this little function of steepness. Arguably, it's a function of just that one thing, just how steep is the graph. And I'm going to show you an example where this interpretation is really, really nice. This came up in a real-world setting for me. And it could for you too, someday, possibly. Here's the story. Let's suppose that you end up buying a house. And of course, architecture is they design all sorts of interesting looking houses, but I'm going to say our house looks like this, let's just say. How would I compute the area of the roof? Potentially hard problem. Right? After all, you've got a triangle here. It's not a right triangle. How are you going to compute the area if it's not a right triangle? I guess you could get up there with a tape measure and measure heights and bases and stuff like that. You could. That's not outrageous. But it would be a little tedious, and notice there's a bunch of, how many faces are there on this roof? And this is a very simple footprint shape of a house, and of course there's plenty of houses that have much more complicated shapes, and there's all sorts of little, tons of polygons making up the roof. So here's the nice observation. The roof is a graph. I can view this as being parameterized by the graph parameterization. Parameterized from basically the footprint, which is a bunch of rectangles, which are easy to compute the area of. That's nice. But but so what? Well, keep in mind, here's our integral for computing surface area. This is my area stretching factor. Notice it only depends on steepness. Now here comes the next key observation here. Turns out, for a lot of houses, all exceptions granted, again, architects can come up with all sorts of clever and cool ideas, and I like that, and that's great and all. But very often, steepness is approximately constant on all of the faces of the house. My house is actually a pretty good example of that. Except for a couple little very minor things, all of the very many faces on the roof of my house are all the same steepness. So that means that this entire integrand is a constants factor outside of integrals, and that means that if I just know the steepness, this little thing tells me what I multiply by my footprint area to get the area of the roof. And that's a much easier calculation. Right? The footprint, after all, it's a bunch of rectangles. Not necessarily even a bunch. It's a short list of rectangles. World's easiest areas to compute. And then just multiply by this factor right there. So nice little trick. Who cares? If you ever own a home, that home may someday need a new roof. You'll be shocked how much that costs. And you might want to double check the contractor's arithmetic, just to make sure that there's not a little oops to the tune of several $1,000s in the calculation. So I've saved myself money by doing this kind of thing in the past. So, anyway, nice trick. Any questions about that? Okay. All right, moving along. So we're going to talk about a new kind of integral now. Talk about surface integrals. What if I have another dimensionally awkward situation? Not a one-dimensional curve in three-dimensional space, but a two-dimensional surface in three-dimensional space. What would I do if there were mass distributed across this surface? Or if there were ants crawling around all over this surface? Or if maybe this is a hillside and there's a bunch of wildflowers all over the surface, and the thing is there's a lot more wildflowers per unit area lower down. I don't know, maybe there's more water down there. There's a lot fewer wildflowers per unit area up higher. Right? Maybe the wildflower density is dependent on height. Right? Highly plausible. How would I compute the total number of wildflowers? How would I compute the total mass of that sheet of metal? How would I compute the number of ants? Whatever. How do I do a chop it up, add it up on a surface? And, well, we're going to write down the exact same idea that we have in previous circumstances. That is a Riemann sum. Notice what this Riemann sum is doing is it's saying on each little piece, let's look, for example, at this little piece right here. It might be hard to count flowers over the entire hill. But on that little piece, it's a small little piece, and I can just tell you how many flowers there are per unit area. And flowers per unit area times area gives me flowers, or ants, or mass, or whatever. So, and then you add that up, of course, over the entire surface, and that tells you your grand total. It's just the same old chop it up, add it up that we've done in every other kind of domain. How are we doing so far? Is everybody with me? Okay. So what kind of an integral is this? Well, it's not a triple integral because there's no volume. It's not a double integral because it's in three space. It's a different thing. So this is what we call a scalar surface integral. The notation pretty naturally comes out of the Riemann sum notation. I think that's all pretty believable. It's just notation. No, keep in mind the Riemann sum is the thing. But anyway, we call this a scalar surface integral. And why scalar? Well, because the differential is a scalar and the integrand is a scalar. Now, this might seem kind of familiar. And it is, you'll notice, very similar to what we did when we were defining scalar line integrals. The whole is the sum of the parts, right? It's just that we're looking at the whole curve. That's the sum of a bunch of little pieces of curve. And on each piece, quantity per unit length times length. add up over the whole. It's very, very similar to what we're doing now over here on surfaces. Is everybody with me? Everybody see the analogy there? Strategically the same, dimensionally different. All right. Cool. Okay, how do we compute these things? Well, it turns out we inadvertently already kind of have. We just have to put the pieces together. Reminder, when we were doing scalar line integrals, turns out we already had. We just had to put the pieces together. Same deal. Parametrization is the answer. Specifically, parametrization is what allows us to view it as an image, and then I can pull back and stretching factor and all that to get an integral in the parameter space. In other words, a T integral. Well, we're going to do the same thing here. We already know how to parametrize surfaces. We already have a bunch of details computed related to that allow us then to pull back into an integral in the parameter space, namely in the ST plane. And here it is. ds, we've previously discussed, magnitude of capital N times dsdt, old formula. Right? We already knew it. It was from the previous section. So we're in business. We have ourselves a formula. If you want to compute a scalar surface integral, parameterize your surface and plug into this formula right here. Okay. A little bit of good news real quick. When you look at this formula, you see that it depends on the parameterization. You can see the parameterization right there, for example. And you can see the parameterization is also kind of wrapped up inside of that capital N vector, which comes from the parameterization, right? In fact, here it is. Here's capital N. You can see it depends on the parameterization. So if this expression on the right depends on the parameterization, that's not good. We wouldn't want this to depend on the parameterization. After all, it needs to give us this absolute quantity, which exists independent of parameterizations, right? So how come the parameterization is all over the place here, and why should the parameterization matter? Cool fact, even though the parameterization is in the formula, it doesn't affect the value. This integral is independent of the parameterization. If you want to see why, there's a detailed discussion in the book, but we're not going to worry about that. Y'all are not responsible for why this expression is independent of parameterization. That's more of a Math 222 kind of a thing. In Math 219, I'm just going to state that it's independent of parameterization, and we just get to use that convenience. We get to use whatever parameterization we want. Okay. All right, let's do one. I'm actually going to do 4. You may recall this. Well, let me flip back. Going back to the line integral calculations. I described a situation of mass distributed across a curve and asked, how do you compute the mass, moment of inertia, x and y coordinates of the centroid, etc. And what we found is it's a bunch of different integrals, but they're different integrals, but they're all on the same curve using the same parameterization with the same stretching factor, mass distributed by the same density, and so they're very, very similar calculations. Well, the same thing is true over here. I have mass distributed across a surface. Density given. I'm going to use a given parameterization. I mean, it's the upper unit hemisphere. Again, we know how to parameterize the unit sphere. And we can use the same calculation for all of these examples to get this stretching factor. And all of that applies to these several calculations we're going to do. So here we go. Get these things to erase. There we go. All right. How do I compute mass? Well, the whole is the sum of the parts. Mass is mass per unit size times size. true for all of these integrals that I'm working with. Right? So I'll tell you what, just because it's always the same for all the rest of these, let me just focus on the one here. Let's see here. ds is stretching factor times d phi d theta. That's our stretching factor formula. That stretching factor we computed up here. Here it is. Stretching factor is sine phi, as we saw a few pages back. So let me stick that in there. Sine phi. A lot of plugging in here. Density formula is just Z. Density is Z. Just plug that in. Wait a second. What is Z? What do I do with this Z right here? Remember, the parameterization is what you're using to plug in, to pull back. So this is X, and this is Y, and, well, this is Z right here. So Z is just cosine phi, straight out of the parameterization. Everybody happy with that? Okay. And likewise for all these other integrals. So, okay. Now, what did we do after examples when we were looking at line integrals? We encountered another application. We decided to think about work. Work is another quantity you can describe if you're going to walk along a curve, you can ask how much work does it take to do so. Maybe you're driving on a mountain road, whatever. How much work does it take to climb to the top of the mountain? And we have a formula that applies on constant vector fields over straight line paths, which we don't have here. But we can chop it up into little pieces, and on each little piece, it's approximately straight, and the force is approximately constant. And on each little piece, then, we can basically use that formula. We're going to take the exact same strategy here for a different question, not work. We're going to talk now, in this context, we're going to talk about flux. Y'all remember this thing called flux. We talked about it a fair amount in Chapter 3. And why do we care about flux? What is it good for? Well, it means different things in different circumstances, but depending on what your vector field is, it computes one or the other of these quantities, and both of them are interesting, right? That volume per unit time of fluid is an interesting thing. Quantity, like mass or population or whatever it is per unit time, also interesting. So depending on how your vector field represents your fluid, flux is always something good. Right? It's a natural quantity of interest in many ways. And by the way, even more than just fluids. And now this is going to have to wait until later on in the sort of near the very end of the course. But we're going to find that even if the vector field is like a gravitational field or an electric field, flux will have very useful applications, and it's a natural thing. Okay. All right. So flux. And again, we have this formula, but that assumes a constant vector field and a flat surface. So we're going to do the exact same thing that we did with curves. We're going to chop it up into a bunch of little pieces on which each piece is approximately flat and small enough so that on those pieces the vector field is approximately constant. And then on each of those little pieces, right, this being that little piece, vector field is approximately constant. We can compute flux with our good old, regular old dot product formula. How are we doing so far? Is everybody with me? All right, so there's a sticky bit here that we need to talk about. Let's go back to the curves business. We had to clarify when we were talking about work on a curve, we need to make sure we have an oriented curve. I need to know which direction we're going. After all, the amount of work that it takes to go up a mountain road is a lot more than the amount of work that it takes to go down the mountain road, right? So it's very, very different. The direction matters all of a sudden. Well, the same is true when you're talking about flux, right? So if I define my flux and compute all of my fluxes based on normal vectors that are like this, then what that means is when my flow is, let's say, like that, if you look at F dot n here, well, the vector field's going approximately the same direction as that normal vector in purple, and so there I would get a positive amount of flux, drawn as this is, and what that means is this flow of the fluid going up through this surface, because this normal vector is pointing that direction, this is the direction of flow through the surface that will count as positive. On the other hand, if the flow were going the other way, if the flow were like this, right? Well, the dot products here between the normal vector and the field vector, well, they're going to be negative. Those vectors are going somewhat opposite-ish directions. And so when the flow is going downward, that will get measured as being negative flux. And we interpret that as negative because it's in the opposite direction of the direction that normal vectors are pointing. So whichever direction your unit normal vectors point, that defines what is the positive flux direction as opposed to negative. Okay. So just like with curves, there's two different options, right? You can go that way along the curve, or you could go the other way along the curve. You've got two options, and we know from previous calculations you're going to get exact negative answers depending on which way you go. The same thing is true here. It's not along, of course, because this is not a curve. It's through. Right? So I've got to set which direction is what I mean by the positive direction through the surface. We call that the orientation of the surface. We need to have an oriented surface. In other words, just a surface by itself is not good enough. I can't make sense out of flux. I don't know which direction you mean. I don't know what to dot it with. Which normal vector do I use? I've got two choices. We don't know, right, without an orientation. So it's only through an oriented surface that you can really talk about flux. And oriented surface then is a pair. It's the underlying surface and then combined as well with that orientation unit normal. Okay, how are we doing? Everybody with me? Oh, and by the way, you could probably guess, and this is true, if you were to orient the other way, if you were to say, hey, for whatever reason, I'm interested in flux downward through this surface, and you define these to be your orientation unit normals, then the flux would be the exact negative of what it was with the normals going the other way. Okay. Alrighty. So, with all this done, we're in business. We're ready to write down our new kind of an integral. We've got this great big surface. The whole is the sum of the parts in terms of flux. On any given little piece, we've already computed that we can just use the regular formula, because on this little piece, now of course I've got it magnified so we can see it better, right? But this is a teeny tiny little piece of area, and the vector field is approximately constant because it's such a teeny tiny little piece of area. And so F dot n times area is ds. So here's our little piece of flux. And this then is what we call a vector surface integral. And this is what we will use to compute the flux of a vector field, a non-constant vector field, through a non-flat surface, or a not necessarily flat surface. All right, are we good so far? And I haven't gotten to this yet. We'll get to that in a moment. Everybody cool? All right. Okay. Okay, so what is the deal with this thing, this ds vector, which you can see here, and you can also just kind of see from the formula, is unit normal vector times ds scalar. Where does that come from, and why do we feel the need to invent a notation to represent that product? What is so natural anyway about the ds vector that I've got defined here? And there's different ways to think about this. Let me go back to the curves, right? And recall all of this business here. And see, I don't think that's very visible, so I'm going to make this larger. There we go. What can we say about the dx vector? The dx vector, different ways you can think about it, but one natural way to think about it is that it's the unit vector t, this is the unit vector defining our orientation, times this ds representing the size of the corresponding piece of our curve. So it's orientation times differential size. All right. What have we got here? We've got orientation times differential size. It's structurally the exact same idea, right? In ds scalar, let's see, let me do it like this. N times ds scalar is natural in exactly the same way as TDS was for the dx vector. So calling this a vector differential in the same way as for curves we called this product a vector differential, totally analogous. Now, here's another way to say it. Different way to say it. This vector dx, you can see it in the picture right here. dx tells me everything I can want to know about this little piece of curve. By its magnitude, it tells me how big this piece of curve is. By its direction, it tells me what the orientation of this piece of curve is. This one vector entirely describes everything relevant about that piece of curve. Okay. Well, what can I say about the ds vector? The ds vector, aka this product here, tells me everything I could possibly want to know about that piece of surface by way of its magnitude. The magnitude is the ds scalar. The magnitude tells me how big this piece of surface is. By its direction is the little n vector, it tells me the orientation of this piece of surface. Again, exactly analogous to the dx vector. So this thing here is deserving of having a name, if only because it's the surface area analog of the dx vector. All right. Okay. Last observation I'll make, and this is kind of a, aesthetic, personal preference kind of a thing, I suppose. But I like there being a clear distinction between what part of my integral is coming from the surface versus what part of the integral is coming from not the surface, something independent of the surface. So, in fact, if you think about it, everything in here, everything in the ds vector, all of this comes from the surface. This is the size of the piece of surface. This is the orientation of the piece of surface. Everything else, everything on this side of the line, completely independent of the surface. The vector field exists independent of the surface. Even if there is no surface, there's still a vector field. And likewise, the surface is independent of the vector field. They're totally disconnected from each other, right? So I like for my differentials to exclusively tell me about the surface, and for my integrands to be the stuff that's not intrinsic to the surface. So anyway, it's just, like I say, it's aesthetics. I think that makes sense, though. All right. And then, of course, now here's the easy appeal. Fewer pen strokes, right? This is the easiest notation between these two options. This is the one that has the least pen strokes. It's the easiest to write down, and so it's nice for that reason as well. Okay, all right. Now, let's talk about how to compute these things. Again, we're already kind of there, right? We have all of this set up. This is all old news. That's just there for recopy, so we don't have to scroll all the time. Nothing new there. If I want to compute, and this is a recopy too. We were just looking at this line on the previous page. If I want to compute these things, how do I compute them? Well, the DS scalar is stretching factor times dsdt. Yeah, question.
Do you need to normalize n after you do the alpha?
Do you need to normalize what now?
The n, like the normal vector?
Oh, you're talking about this capital N vector?
Yes.
Capital N is not a unit vector necessarily, and its magnitude matters. After all, it's its magnitude that is the stretching factor. Yeah. Does that make sense? So you want to make sure to distinguish between capital N, whose magnitude is very important, right, versus little n, who needs to be a unit vector. And that's why we use one capital and one lowercase. They're not the same.
So the magnitude is the stretching factor, and the little n is defining the flux, right?
The little n, it defines the orientation, and you can use it to, among other things, compute the dot product that's part of the flux. That's right. Yep. Is that cool? All right. Cool. Okay. So, yeah, all right, we've got all this stuff. We know that ds is this thing. That's our stretching factor calculation. And now, before I go on, I'm going to give a confession in advance. I'm about to claim that this is equal to that. I'm going to sweep a subtlety under the rug. I'm doing it on purpose. The reason I'm sweeping the subtlety under the rug is because we've got a lot going on as it is. There's parameterizations and partial derivatives and cross products and stretching factors and parameters and pullbacks and oh my god, there's a lot going on, and we don't need yet another subtle complication right now. So I'm on purpose deliberately going to sweep a point under the rug so that we can get down to an example, get a victory on the board. Let's get one in the win column, and then the subtlety we'll come back and talk about later. It probably won't be today. But anyway, with that confession noted, let's think about what this is. This product here, that's the direction of the normal vector. This is the magnitude of the normal vector. The product has the same direction as the normal vector, has the same magnitude as the normal vector. It's the normal vector. It's capital N. All right, easy appeal. Everybody buy it? Again, fully confessed, I have committed a math crime here. I did it on purpose. We'll fix it later. But easy to buy as a broad stroke. This resulting formula, by the way, there is a concern about it. There is an asterisk, but still, I'm going to leave it as being an equivalent formulation of these things, and we'll deal with the asterisk later. So, altogether, this notation, most easy to relate to applications. This formulation, it's the most compact, it's the most mathematically natural, one could argue. That's nice. And this one right here is going to be the one that's most easily computed from. So all of these notations have their merits and their sort of benefits. Okay, all right, so easy example. If I want to compute a flux, I've got a vector field, I've got a surface. How do we compute the flux? Notice I'm going to plug right into this brand new formula that we just motivated, and it's kind of a matter of doing it. Now, of course, we have to parameterize. Right? All of what came out of here comes out of the parameterization. So graph parameterization, thankfully this is a graph. That's the graph parameterization. Partials, a little bit of calculus. Cross product, a little bit of algebra. We don't even have to take the magnitude, do we? Isn't that nice? Isn't that weird, by the way? It's a little bit of an eyebrow raiser. When we were doing scalar surface integrals, we had to compute the magnitude of that. For vector surface integrals, you don't need to compute the magnitude. You just need the vector itself. How nice. It's just a matter of plugging in. So our normal vector that we just computed goes here. The vector field that we started with is this thing, believe it or not. Now don't forget, you have to plug in from the parameterization. So for example, let's see here. What do I do with this z? Right there. Well, don't forget, this is z. Right there. And so it is, when I say z squared, right, looking at this vector field, first coordinate z squared, this is what z is, squared. Is that cool? Everybody happy? All right, likewise for the x and the y that follow. Plug and chug. It's a matter of computing this integral at this point, and it's a pretty straight up integral. Nice constant bounds, polynomial integrand. That's easily computed. Okay, we're out of time. We will pick up here next time. I'll reveal what my crime was, and we'll fix it and move along. See y'all later. Have a good one.